Well, first of all, thanks for the kind introduction by Mike Falk. It has been a pleasure to meet all the guys of HDF5 many years ago. They helped me a lot at the beginning when I was trying to establish myself as a freelancer. Also, I am very glad to be here among so many friends like Elena and Andy. Thanks for inviting me to talk about the project that I've been working for the last couple of years in collaboration with my colleagues. So to start with, I want to talk about Caterva, which is a compressed and multidimensional container for not so big data, and that means that Caterva is especially meant for being an in-memory compressor. So let me explain what an in-memory container means. So a few words about me. I am a physicist by training, computer scientist by passion, and I am an open source enthusiast by philosophy. My first serious open source project was PyTables. I stopped working on it, but still I am in the committee for maintaining it. And the project that I've been working most of my time lately is Blosc, the compressor that came out of trying to make PyTables as fast as possible. And I am very happy that Blosc is being used in the community quite a lot. So PyTables was like a wrapper on top of HDF5, but it was a bit more than a wrapper. And in particular, it included queries, which is one of the reasons why PyTables is supported by default in pandas. And PyTables is still used a lot, especially in the pandas community, for doing queries very fast on tabular data based on HDF5. Okay, so let's go with the meat of the presentation. What's Caterva? So Caterva is an open source C library and a format that allows to store large multidimensional, chunked, and compressed datasets. Data can be stored either in memory or on disk, but the API to handle both versions is the same. And compression is handled transparently for the user by adopting the Blosc2 library, which is the next generation of Blosc that I am going to talk a little bit about. So why another data container? Well, truth is that most of the existing data containers supporting on-the-fly compression are meant for on-disk and cloud data. But we had like a special needs, and for me, the memory layer can be also seen as a storage too. And in my opinion, there is a strong need for a container that is optimized for the memory layer, or layers that are very fast, like extremely fast solid-state disks, for example. So Caterva is designed from the ground up to use the memory layer as a storage for a compressed data container. So just to position Caterva is meant to be like to address the need to be a data container for memory or for very fast solid-state disks. Whereas other containers are more focused on solid-state disks, mechanical disk, and maybe also cloud storage. And why another format? Well, being able to store in an in-memory data container doesn't mean that data cannot be persisted. It is critical to find a way to store and retrieve data efficiently. Also, it is important to adopt open formats for reducing the maintenance burden and facilitate its adoption more quickly. As we will see soon, Caterva brings an efficient and open format for persistence. So the main feature of Caterva is to get a slice of multidimensional data very quickly. Of course, if Caterva is based in memory, we want to do that as fast as possible. And the resulting slices can be either Caterva containers or regular plain buffers for better interaction, for example, with NumPy. So those of you, I am pretty sure that all of you are very used to manipulate chunked multidimensional arrays, and you know how critical choosing the partition size is, right? So I am going to present a small, but I think it's a representative benchmark. You can see the benchmark here. It's a Python notebook, and the Python notebook is like this one. So you can run it, and you can play with the different parameters. So for example, I've been using different data containers, and I've been using Blosc for maximum performance in all of them in order to compare pairs with pairs. Okay, so let's go with the results. So for in memory, we can see that HDF5, as you probably, not a lot of you, but HDF5 also supports store data in memory via driver. So we can see that Caterva can write data pretty efficiently in memory. But the most important thing for us is that Caterva takes every measure to reduce the number of copies in internal buffers, in internal pipeline for compressing and decompressing. And we can see that Caterva has an edge in performance for getting slices, random slices in this case, from hypercubes. Caterva is also able to run from data that is on disk, but it is not yet optimized for that. And in fact, we can see that there is still room for optimization when reading from disk, which is great. But this is not our big priority right now. Okay, having said that, let me show you a very brief introduction to the C API for Caterva. As I said, Caterva is a pure C library. So in order to create a data container in memory, we just create a new context here with different Blosc compression and decompression parameters by default. And we create the partition shape, which is in HDF5, it is the chunk shape. And then here is the actual shape of the data set. And we create the dimensions for that. First, we create an empty array without the final dimensions. And then we can assign the dimensions. And we create a buffer here. And we introduce this buffer. We populate the new container using the buffer with this code. So the API is pretty easy to get. And this is also another example for how to get an slice out of the data set that we created. So we define the dimensions for the shape that we want to retrieve, like the start, the stop limits. The steps are not yet implemented, but probably will come later. And after this is created, we create a container for getting the slice, and we get the slice by using Caterva get slice, and we populate cat2, which is empty, from the slice that fulfills the start and stop from cat1. So we then squeeze, so all the dimensions that are degenerated, like they are ones, for example, they can be squeezed like this to get rid of the degenerated dimensions. And then we just print the results by converting the Caterva container to a buffer again, and then just print the results from the buffer. Okay, so this is an example of the C API. Now let's have a look at a brief comparison against well-known chunked containers. For example, I took here like HDF5, ZAR, which is a nascent data container, which is also based on Blosc. It uses Blosc by default, and also Caterva. So probably the most interesting thing here is that, for example, HDF5 can have like many data containers per file. ZAR, it's quite different. It needs to have like 1 file per chunk, but Caterva can allow 1 file per container, which tries to address the limitation in ZAR that is trying to host 1 file per chunk. Then both ZAR and HDF5 are hierarchical, but Caterva is not hierarchical, so you need to use the file system in order to fake the hierarchy. Both ZAR and HDF5, we can say that they are mature, but Caterva is in process. And both and all three have in-memory versions, although Caterva has versions for the containers that can be sequential in memory and sparse in memory. And this is going to be important, this distinction. So let me say a few words before proceeding more with Caterva about Blosc2, because Caterva is strongly based on Blosc2. So Blosc2 is the next generation of the well-known Blosc, and the new features are that it supports enlargeable 64-bit containers, either in memory or on disk. It comes with new compression codecs, new filters, the concept of MetaLayers that I am going to explain, and also it provides support for user metadata. So let's, and just to give you an overview, most of you will know Blosc, but let me remind you that Blosc can be used to compress and decompress, but especially decompress very, very fast. And in this independent benchmark by one of the main authors of ZAR, we can see that Blosc can decompress data even faster than a regular memory copy, even when we have like very big compression ratios, which is pretty amazing. Okay, so let me say a few words about the containers in Blosc. So we have, in one hand, on the left, we have the super chunk, which is the container, which is the default container for in-memory data. And then there is a frame, which is the default container when we are storing data on disk. Okay. So the super chunk, essentially, it comes with different, with a header, where it stores the codec, the filter pipeline, and different other parameters. Then the MetaLayers, and then a series of pointers that points to the chunks in different areas of memory. And these chunks are sparse in memory. This is important because when you want to make an efficient use of memory, you cannot, and you want to deal with big data sets, you don't want all the memory, all the store to be sequential in memory. The system typically can do a better job if the chunks are sparse in memory. When you are, on the other hand, on the right side, when you need to store the data on disk, you need, of course, something that is sequential. So there is a frame format for storing what is in memory. Okay, and this is there is a header. There are the chunks. There's a chunk index for accessing very quickly to the different chunks, the user metadata, and also in the end a fingerprint for making sure that the data that you stored is not corrupted, for example. Okay. So I mentioned already MetaLayers, the MetaLayers concept, and this is a central concept in Caterva. So let me explain a bit what a MetaLayer is. MetaLayer is a part of Blosc2 actually, which is small metadata for informing about the kind of data that is stored on a Blosc2 container. And they are handy for defining layers with different specifications, like a layer for multidimensions. We can speak another layer for data types, another layer for geospatial things, whatever. So the global picture should be seen like this. So in the bottom, we can see the Blosc container here. And then one first layer could be like Caterva that adds a multidimensional meaning to the data that is stored in the Blosc container. And then we can also implement another MetaLayer that could be like a multidimensional plus type. Okay. We didn't integrate the data type in Caterva because of strong reasons that I am going to explain later. And then, for example, we can imagine that we can add another layer on top of first layer which adds specific things that could be appropriate for microscope or for different things like microscopy, astronomy, geospatial, genomics, nuclear, and machine learning as well, or whatever, or even finance. So the multiple layers, it's add the capability to target different data aspects. So let me go a little bit on detail on the Caterva MetaLayer on top of Blosc2, sorry. So this MetaLayer is very, very easy. So it's just it's a serialization of this struct, which is the number of the dimension of the dataset, the actual dimensions, and then the partition dimensions, which is the equivalent of the chunk dimensions in HDF5. So this is the only information that is required by this layer. And the MetaLayers in Blosc can be modified so that the shapes can be also updated. So an array can grow or shrink in the same way than HDF5 as well. So I mentioned before that Caterva is type agnostic, but why so? Well, the fact is that there are too many data type systems floating around, and in our opinion, multidimensionality is orthogonal to the data type. And this is essentially the reason why we decided not to make the type part of the Caterva, and we rather try to provide a way for the interested parties to define a MetaLayer for endowing the desired type system to the data. And this is very easy to do, and you can have a look at how it works on this example. It's a Jupyter notebook example, and you will see it is using Cat4Py, which is a very shallow wrapper for Caterva for Python, and you will see how easy it is to add another MetaLayer for Caterva for storing types. And of course, the frame format and MetaLayers specifications are completely open, and they are specified here in the project. So this is the frame format. So there is a header, the chunks, and the trailer, and all the header section is completely specified byte by byte, and it is using the message pack format, which I found very, very convenient to use for defining a binary format for Caterva. So even everything is described even at bit level. Okay. So also the format for the Caterva MetaLayer is also described at the byte level. It's much simpler than the Caterva layer. But that means also that anyone can produce, for example, a small program in another language than C, for example, and try to read the information from here because it's completely specified. Okay, so one last feature about Blosc2. Blosc2 has this capability to store user metadata that can be variable in length. So the user metadata is the equivalent feature to HDF5, the attributes in HDF5, where you can store different aspects that complement your data, like temperature, pressure, or timestamps, or whatever thing that you can serialize in message pack. It is not mandatory to serialize things in message pack, but this is strongly advised that you use message pack because it's very, very portable. Okay, so let me finish with a few examples where Caterva can help. So whenever there is a need for deal with dimensional datasets as fast as possible, Caterva is a very interesting thing. Also for providing a backend for other packages, like for example, bcalls, which is a tabular data storage that I created like some years ago, and also for ZAR. And in fact, we are in conversation with the ZAR people in order to make a new generation of ZAR maybe based on Caterva instead of using Blosc2, because Caterva can help also in performance for ZAR. Also, Caterva is written in portable C99, so there are no limitations to be wrapped for other languages than, for example, Python. And also, Caterva allows to create different MetaLayers that adapt to users' needs. And this is a question for you where you can help. Of course, Blosc2, Caterva, and Cat4Py are all open source, so you can always contribute with ideas and code. But if you like the concept behind the project, but you don't have time to contribute with code, please, you can do a donation to Blosc project via the NumFocus Foundation. I am proud to say that Blosc is a NumFocus sponsored project since I think it's April this year, and NumFocus already gave us a small grant that allow us to get Blosc2 out of beta. Out of alpha, and it is in advanced beta state right now. So thank you for NumFocus for helping the development of Blosc and Caterva. So to wrap up, Caterva is a C library and a format for handling multidimensional data on top of Blosc2 containers. And the main goal is to efficiently leverage fast storage like memory, but not only memory, but for example, persistent memory like Intel Optane, which is kind of very fast memory, but can be persistent as well, or fast solid state disks. You can use MetaLayers. The MetaLayers, as I said, the MetaLayers concept is central to Caterva and to Blosc ecosystem, because you can use them for adapting Caterva containers or in general Blosc containers to your own needs. Here are the links for the Caterva and Blosc projects that you are welcome to contribute. And I would like to also thank you, a big thank you for Aleix Alcácer, who contributed most of the code behind Caterva as a part of his degree thesis. Then Christian Steiner for suggestions and improvements on Blosc2 and Caterva projects. Aracil for his proposal for using message pack for serializing Blosc2 containers. I am very happy to use message pack. It's really useful. And of course, NumFocus for providing funding for developing Blosc2 and Caterva. So thank you. If you have any questions, I will take them. I think I have a pending question from Ivan Esmirnov, and that maybe I can answer right now, and then you can proceed with other questions.
Yes.
But I think Ivan. So Ivan, I think I understood that Ivan is using Blosc in H5Py, and he's worried that the support is not kind of official in H5Py. Is that correct, Ivan? Yeah. Well, I don't hear Ivan, but I can say that I think he was worried about possible license issues in merging Blosc inside H5Py. I can say that there is no problem at all with the license of Blosc2. Blosc2 has a very open BSD license, so anyone, it is designed, in fact, to be included in any library that wants to include the sources. If this is going to help the H5Py, then it is. I am very happy if people start to do that. The problem is that someone has to do that, and probably there is not a lot of manpower or people that has free time for doing that. But this is not a problem of license. This is a problem of more time for implementing that. Okay, so with that, I will take other questions if you have them. Thank you.
Comments? Okay. Oh, wait. Ask a question. Related to sparse data, how would you compare this using, say, HF compression versus your format versus maybe a more explicit sparse data definition?
Did you hear that, Francesc?
No.
I think speak in front of this mic, maybe.
Okay.
Yeah. Francesc, can you hear me?
Yeah.
Yeah, I was asking for sparse data.
Yeah.
What's kind of the pros and cons using, say, HDF5 with compression versus the Caterva versus, some kind of more explicit sparse data structures?
You mean sparse data, like, for example, big multidimensional with a big arrays with a lot of zeros inside, right?
Yes, exactly.
Okay. Yeah, I mean, this is not something that we are. I mean, we had to deal. I suppose the short answer is that compression can. I mean, Blosc is a very efficient compressor, so you can pass all the zeros to the data container and hope for Blosc to reduce the zeros. I mean, Blosc is really efficient compressing zeros, of course, and that could be a fair solution. But there is not explicit support for sparse as such. I suppose that a good thing would be to just to come with a format for expressing the sparse data and then store that in regular data containers. Although you will lose the multidimensionality capabilities of Caterva, of course. So you can take both approaches, but compressing zeros, or just store them dispersed in a linear data container.
Okay, all right, thanks.
Mm-hmm.
All right, thank you, Francesc.
Thank you.
As always, helping us open our minds to new things. Thanks a lot, Francesc.